I'd like to show you a really simple illustration of what's happening inside stars when they collapse down to be these compact objects. So I want you to just think about a gas normally. Normally a gas is a whole bunch of atoms, and they all have some temperature collectively, and they're all moving around, bouncing around and around. And we'd say that they kind of bounce off each other, but they really are never actually touching each other. So an atom we can think of as a nucleus in the center, and a whole bunch of electrons going around, which are these lighter colored dots I've drawn here. Now, it's true of anything in ordinary life that's touching each other, like even when you touch one finger against the other or your hand against the table, you're not actually in contact. What's happening is, as the atoms from one object approach the other, there's a repulsion, right? The electrons on both atoms are pushing away from each other because they have the same charge. And so if this atom were coming in from ways, maybe this is your hand coming towards a table, or it's two gas atoms inside a star, they're coming towards each other, and as they approach, they start to repel, and they kind of bounce off each other without ever actually touching. That's what happens for most of a star's life. As gravity's pulling things close together, they get really close, they bounce off each other, but they never actually touch. Well, once the fuel inside the star runs out, the gravity starts to pull it in tighter and tighter and tighter. And what happens is, here I can illustrate this nicely, the atoms get closer and closer together. And even though they're repelling each other, oh, they're pushing so hard against each other, gravity still pushes even stronger. Gravity pushes to the point where I gotta make this work just right, because they actually end up physically touching each other. So let me draw right around this thing and bring it in so that it touches. That is, the electrons get right next to each other. We call it electron degeneracy. And that's a really strong force pushing back out against gravity. So the electrons are pushing right up against each other, and that's what holds up the white dwarf star. So the electrons, the whole atoms, are right up against each other, more dense than anything imaginable, pretty much, right? Extremely, extremely dense. Now, when the star collapses that much, it gets down to be about the same size as the Earth. So imagine like the mass of the whole sun collapsed down to the size of the Earth. I mean, when that happens, like a teaspoon of that star stuff would weigh about a ton. Here, you know, if we normally think about gravity, right? It's incredibly dense. But now, if a star was even bigger than that initially, the gravity's so strong that not even the electrons pushing up against each other can actually hold it up. Instead, what happens is the electrons basically get shoved into the protons in the nucleus of the atom, and they essentially disappear. So if the star was so big initially that it collapses beyond a white dwarf, or let me erase all this electrons, all that's left essentially is the neutrons in the center of the star. I mean, the atoms basically get ripped apart and annihilated, and all you have left is the neutrons. That means that the star can collapse even further, right, closer together. So let's do that, right? This is now, we've moved beyond a white dwarf, and now we're approaching what we call a neutron star. Boom! The neutrons at the center of the atoms are right up against each other. Electrons are all stripped away. Now this star, this large star, has collapsed beyond the size of the Earth, even smaller, down to the size of just a city, right? And that's what we call a neutron star. And it's held up because the neutrons themselves, these parts of atoms, there's not even a whole atom anywhere inside the star. It's only pieces of atoms, neutrons, that's holding up the whole star. Now the gravity is just absurd. Like if you had a teaspoon of neutron star, it'd be like 20,000 tons or something crazy. All right, so, but there are some stars that are so big that even this neutron pressure pushing back is not enough to hold up against gravity. And what happens then? The neutrons annihilate one another, and the whole thing disappears. But what doesn't disappear is the enormous gravity. And so we're left with a black hole, this infinitesimally small, smaller than anything you can ever imagine, so small it essentially does not exist, yet it has the gravity of an entire star. I mean, this is like crazy, right? This is crazy. Well, these are the three types of compact objects: white dwarfs, neutron stars, and black holes. that we're going to look at. And I just want to show you some pictures. White dwarfs are one of the only things that we actually have pictures of. So I showed you this before. This is the Ring Nebula, which is a planetary nebula, right? This is a star like the Sun that's exploded outward. And we can actually see in the very center, this is a picture from the Hubble Space Telescope, in the very center of the Ring Nebula, you can see that little bluish star. That is the white dwarf. That is a star that's about the size of the Earth. That's still really hot and glowing hot. But it's so small, right? And it's this core held up by the electron pressure. This sort of like ashes of this star that once was. So it's pretty crazy. As we learn more about these compact objects in this lesson, we're actually going to see some of the evidence for neutron stars and also for black holes.